with you guys. If you guys can't see, then we'll try something else. But this is okay for now. Okay, so today is to quantify or to learn more about these Coulombic laws, to get an understanding of how things become electrostatically charged. We talked about that last class, and how they're transferred. I have this here for you. I want to know which one you think is wrong. Sorry, which one you think is right. There's one right answer, 3 wrong answers. Take 2 minutes. Whoops, I'm going to do that again. Take 2 minutes to read them and tell me which one you think is right and why you think all the other ones are wrong. You can discuss it if you want. That's no problem. Okay, tell me, is Yoshi right or wrong? Wrong, why? Someone explain to me why.
Metal isn't always charged because sometimes we need to put friction on the charged.
Okay, so there's 2 things in it. Does it have free electrons? Because metal is a conductor, it does have free electrons. We'll talk about that later today, about conductors and insulators. So yes, it does have free electrons, but it doesn't mean it's charged. What does it mean to be charged?
The number of electrons is more than
Or the other way around. The number of protons is more than the number of electrons. Exactly. And it's not necessarily true. This one's not charged. There's nothing there. Okay? All right, so Yoshi's wrong. Mario, in a metal, both the positive and negative charges will move. Right or wrong? Why? Exactly. Protons don't move. It's the electrons that move. So Mario is also wrong. Bart, right or wrong? This one is trickier. This one is the one that I took there to see if you guys are paying attention. So right or wrong? Okay, why? Exactly. The statement, other than that, is totally true, except that positives don't move. So it leaves us with this. Maybe they're all wrong. Who knows? So if you put positively charged rod near wires, their free electrons will move toward the rod. Is that true or not? That's true. It is electrons that move, and there are free electrons. So that would be it. Okay, perfect. Here, it's that machine, the electroscope that we, not the machine, but the device, the electroscope device that we used last time. I'm bringing a charged rod next to it, kind of like we did. All I want you guys to tell me is what's going to happen to the charging, okay? So I have it drawn over here. When it's far away, what do the charges look like on the electroscope? It's neutral, but there are still charges, still positive charges and negative charges. Overall, exactly. Overall, it's neutral, and in order for it to be neutral, they have to be evenly distributed. So what you guys can do is you guys can write pluses all over the place and negatives in an equal amount all over the place. So you just have to make sure there are the same number of positives as there are negatives. All right, once you bring that rod close to it, then what happens? Is it touching, first of all? Yeah?
The electrons will
Okay, so the electrons move closer to the top, so they reach that metal plate. And where do I draw the positive charges here? At the bottom? Exactly. It's actually everywhere because we said that protons don't move. So it's positively charged everywhere except near the top, the electrons are neutralizing them, leaving the bottom part not neutralized. Therefore, the bottom part is positively charged and they will repel each other. Okay? So to show that they're repelling each other, I'll draw vector arrows going in opposite directions, and the force I'm going to give it is the electrostatic force, Fe. Next, this time I'm going to touch it, and what's going to happen? Show me which charges are where. So we're going to draw on the second one here. We're going to draw over here. So what do I need to draw? This time the rod, the positively charged rod, touches the electroscope. What's going to happen? Actually, just wait, because you answer a lot, yeah. So Maxime, I want you to try. Oh, crap. Okay. Yeah, so the rod's going to become, or less positive. So does it still have positive charges? Yeah, absolutely. Are there any positive charges on the electroscope? Oh, negative charges. I'm sorry, negative. Are there any negative charges on the electroscope? Probably not. I mean, it all depends on the number of charges. But essentially, if the rod is massively positive, then it's going to take all of the electrons out of the electroscope. So I will leave it like this. Okay? Everyone's okay with this? This is just the same thing. Okay. So now let's try this with a negatively charged rod, and you're touching it. So what are you doing this time? What's happening? Can everyone see? You're behind a pole here. You okay with that?
Yeah, it's all good.
Okay. So you have a negatively charged. Yeah, go ahead. Yeah, the electrons are going to go to the rod to the electroscope. And so this is going to become negative. And then what's going to happen? Are the two parts of the leaves going to go far apart from each other? In this case, yes, because you're assuming that it was neutral before. Yeah, but because negative repulse is negative, just like positive repulse is positive, then yes, they will go outwards as well. And that's the same thing. It's still electrostatic force. This is just review from last class. Like this whole part, everything we've done so far is just review. Here's an explanation of that. If you need it in official terms, you can consult it. Now, there's a couple of things we didn't talk about last class that we need to talk about now. Oops. There's a difference between an insulator and a conductor. Now, what is that? What do you guys know about these two terms? Give me an example. Yeah, go. Tell me what the term conducts means for you. It doesn't have to be an official science definition for you. Electrons can pass through it. In order for the electrons to be able to pass through it, what does that mean? Does that mean electrons move freely or do they not move freely? They move freely through conductors, all right? And so let's just write that because that's really important. In a conductor, electrons move freely. Okay? And let's say, I'm not going to turn it on or anything like that, but let's say this thing is on and it's positively charged, right? And I touch it here, right? And then I remove it, just like we were doing. This is positively charged now, right? Is it? I mean, it doesn't work. Let's say it was negatively charged. Let's say I touched it and it became negatively charged. Would the negative charges stay where the contact point is, or would it distribute evenly all around? It would distribute evenly all around because it's a conductor. This is metal, it's a conductor, and it's going to allow the electrons to spread out evenly. If I have a balloon, is that an insulator or a conductor? Yeah, a balloon is an insulator. And let's say I rubbed it on someone's hair, and this part is the part that I rubbed, and that's where the parts are negative. Is it going to stay there, or is it going to distribute? It's going to stay there because the electrons are not free to move. Okay? So let's write that down. So in an insulator, electrons are not free to move, and we're going to give examples of each. Electrons are not free to move. An example of this would be metal. An example of this would be rubber. Let me ask you guys another question with this rod. Again, let's go back to this being positive here. So imagine this thing is positive again. I'm not going to turn it on. I touch it. Nope, forget it. This thing is on, and I bring it close. If I bring it close, where are the electrons? Where are the protons? Are the electrons here close to it, or are they freely distributed because of the because it's a conductor? It's going to become closer because now there is a force pulling them. They're free to go from there to rotate around and come here and localize there. They're bound to there until I move it away, and then they're free to go back again. All right? Whereas the balloon, after I removed it, it didn't go back again. Okay, that's the difference. It's not so important now. You're going to see that when we do electric potential and Gauss's law later on, that these insulators and conductors are going to become important. Okay? Another thing we didn't talk about that's super important is how to charge an object. We did it. We used some ways to charge objects, but we didn't actually officially write any of those down. So which ones do you know? How did we charge objects? Friction. Friction is the first one. Do you guys know why friction causes an object to get charged? Yeah, but how? Why? Why does it physically do that? But why? Not the atoms, that's too big. It stimulates the electrons. So by rubbing that, you're energizing the electrons, and they're going to go towards the more electronegative atoms. All right, so in the case of the balloon in the hair, you're making the friction, you're stimulating the electrons in the hair, and they're entering the more electronegative balloon. Okay, simple as that. So stimulated electrons move towards electronegativity. Yeah? Yeah, good. So next one is induction. What's induction? That's the hardest one. It came up second, but that's the hardest of the three. How do you charge something through induction? Do you guys know what induction means? Yeah.
That's when you bring something that is charged close to something that isn't.
Okay, so let's talk about this again. I'm just going to turn it on because it's just more fun to hear it. Oh, okay. The charge of this? Charge of this? Neutral. The charge of the rod? Still overall? Oh, Jesus. Excuse my language. The rod is still neutral overall, but it's localized differently, right? Negatives here, positives there. Everyone's okay with that? If I bring it out, this is neutral, right? I haven't touched it. If I touch it, it's a different issue. In induction, before we talk about induction, what I'm asking about is things that are able to charge other objects. Did I really charge this if I brought it back and it was still neutral? No, I didn't charge it. Okay, so that's not induction, all right? So what is induction? I'll give you a hint. There is no contact with that. So how do I charge this thing inductively? With a wire? Very good. What do you mean by that? Who said that? Oh, sorry. So you're saying the wire is between that and this? Yes. No, there's no contact between that and this. But a wire is a good answer. You can do it through a wire. How? Yeah. Where do I attach the wire? I attach it together? Okay, there's no attachment together. That's not what induction is. That would be the next one, which you would be writing. Yeah. Yeah. Exactly. All right. So Leo's got it perfectly right. What does that mean? So let's say this thing is on. I bring it here. Attach a wire there. What's going to happen? Leo, you want to explain it?
Yeah. But it's not going to do anything if you put it there because all the electrons are on the other side.
The electrons are there?
Yeah.
Okay, so where do I need to put the electrons? The wire, sorry.
You put it there.
There? Okay.
So all the electrons would go down to the wire.
But they're attracted to this then?
Yeah.
So they wouldn't go down the wire? Yeah. Okay, so that maybe we need to improve it a little bit. What do you think?
Maybe if you attach the wire on top, the electrons will go the other way.
So it's attached to the ground, and then the ground's giving it electrons? Absolutely. Okay? So you attach a wire to this end here, all right, to the ground. And the ground, remember, has an excess amount of electrons, has an excess amount of protons. It never needs to worry about its charge because it's the planet. It's got a whole bunch of charge. All right, so the wire is attached here. This part's negative, this part's positive, so it's going to start attracting electrons through the wire and into this. All right, and then what do I need to do if I want to charge this? Do I move it away? Or do I remove the wire first? Yes, remove the wire first. So now it doesn't, the electrons can't go back into the ground. And then if I remove this, theoretically, this should have excess electrons. You guys get what I'm saying? Okay, let's write that down. Connect polarized object to a ground, then remove the ground to keep charges. Write it in your own words because this is not complete. I don't have enough space to write everything in. Yeah. This would have been a polarized object because there was the pole, there was a positive pole here, the negative pole that was getting attracted by this, and then on the top had the opposite pole, which would have been positively charged.
It's just the polarized, that's the polarized object.
Exactly. Correct.
Last class, you said the definition of a ground is, didn't you say it was like where the electrons go?
You're right. I did say that. The more technical definition would be just literally attached to the ground.
Okay. So
Yeah.
this is
Yep. All right, and the third way of charging an object, someone said it, yeah? Conductance, yeah. And that's by literally being attached to something that has a charge, okay? So being attached to something that has a charge.
Could be attached to another object that's charged, but not necessarily become charged.
That's true. But I'm saying if you become charged by connection, then that's a form of conductance. So for example, me touching this, what are those three, is it? Is it friction, induction, or conductance? That would be conductance. Okay? How is this getting charged? By friction, because they're moving down. Okay? If I were to do this, tell me what would happen. Oh, it's going to hurt. So if I go like this, all right? I go like that, and then I go like that, and then I go like that. What is the charge here? Neutral? Yeah, correct, neutral. What could I, like, if I did this, what is the charge now? Negative. Wow, you guys are really fast. That's impressive. Good job. What was the difference? So how am I charging this? That's what kind of charging? That's induction, because I'm the ground. Okay? And if I were to touch this, that would be conduction. That thing is charged by friction. There's your three examples of three different things. You good with that? Okay. Lightning. Which one of those three is it? Friction. Yeah. Yes.
Can you explain why it is charged positively by friction?
This?
Yeah.
Okay, so there's friction happening, all right? And so there's going to be a separation of the charges. The electrons are moving through the wire. This thing is called the ground, and it's going into there. And this is grounded to the building, and the building is grounded to the ground. Okay? So what's left here is a positive charge. Okay? Yeah? Yeah? That's a very good question. Who wants to answer that? So let's say a charged object has 100 protons. How many electrons can it absorb? It can absorb 100, because after that, it's neutral, and there's no more electrostatic force. Okay? Which is a great segue to the next section. Any questions on this? We're about to get really mathy now. You guys okay with that? Yay for math. Yes, math is the best. Okay, so bring out the third PowerPoint, please. It's going to be called Coulomb's Law. You guys want to take a 2-minute break?
Yes, please.
Yeah, go. 2 minutes. Let's go.
2 minutes is all.
Yeah, stretch your legs. We'll have more breaks. Promise.
Is it possible that when we're not having labs, have the classroom with chairs?
Yes, I'm looking into it. Because it's a matter of which other classrooms are free downstairs. I'm looking into it. I know. It's the worst. Yeah. Ouais, je sais. Non, je comprends complètement. Hey. Okay.
It explains that I have a special measure during exams or labs.
Okay, perfect.
Lab exams.
Perfect.
Just because of my anxiety, so it might not be necessary every time, but
okay.
sometimes.
Perfect. Thank you for telling me. All right, let's get started. All right. So Coulomb's law. Coulomb's law is just basically a formula. It's an equation that Coulomb came up with that describes the magnitude of the force between two things. So we're going to be able to apply this today. There it is. That's your equation. All right. We're going to be using this so much, and we're going to be deriving other equations from this. So please get familiar with it. It's very simple. All right. F is what? You tell me. Force. That's the easy part. You can call that electrostatic force if you want. And then there's those two Q's. Did we talk about what Q was last class? No? Q is charge. Okay? And when you're talking about a force between charged objects, how many objects do you need to have in order for there to be a force between them? Two. So it makes sense that you have two charges here because the charge of both objects is very important. So there's your charge of object 1. There's your charge of object 2. Object 1, object 2. Okay? What's also really important when you have two charged objects? If this was charged, Gabriel, could you hold it? Is there going to be a force of attraction between that balloon and this? Let's say that not really. I mean, if this was negatively charged and that was positively charged, there would be a force of attraction, just it would be really much lower than if it were here. So what is an important aspect of this force? Distance. And is it the greater the distance, the more the force, or the greater the distance, the less the force? Yeah, so it has to be on the denominator, just like it is over there. So R would describe the distance between the two objects. And it's a squared relationship. All right? No. There. Okay? And K, that's a constant. And you have it written there as 8.99 times 10 to the 9. I'm okay with you guys rounding it to 9. So 9 times 10 to the 9. It's a very easy number to remember. If you want to punch it in your calculator, you can do 9e9. 9, so I'm going to call it 99. Okay? It's an easy way to remember it that way. Yeah.
So the law is to find the electrostatic force between two objects.
Exactly, to quantify the force between two objects. Yes?
Should we memorize it? The constant?
The constant? Ugh. No. I'll give you guys all the constants and equations. There's no point in memorizing them. We good? Yep. Okay, no problem. While I'm waiting, I want you guys to answer some questions for me. What are the units of the distance between two objects? Meters, okay? So we're in physics class. It's in meters. What about the charge of objects? Coulombs. Okay, very good. Force? One more question. Is this force a vector or not? Yes. All forces are vectors. Just automatically, from now on and for the rest of your life, forces are vectors. Okay? We're good? Have you guys seen this formula before? Universal law of gravitation. What is this term here? Whoops, not that term. What is this term here? What's that? No. So what is, I'm going to stand back here because I seem to be blocking other people over there, not because I'm watching over you guys. So what is that term? Did you guys learn about gravitational field? It's the what? Acceleration? Yeah, okay, yeah. If you do all the calculations, it approximately gives you the acceleration. On Earth, it's 9.81, But in fact, now is not a good time to talk about it. I'm going to talk about it next week. Yeah. It's called the gravitational field, and it's important because there is something called an electric field. Oh, crap. All right. But you can see the similarity, right? Like there is a constant. There's interaction between two objects. Whoa, why is it so slow? Yeah, there's a constant K, interaction between two objects, Q1 and Q2, and the distance between them. Very similar to this. There is a constant, universal gravitational constant, the interaction between two objects, M1 and M2, and a distance between them. Do you guys see the similarities? Thank you. So here, let's just fill these things out because it's important to understand the similarity. There's going to be a third one, a magnetic force, which is also similar to this. We're going to, at the end of the year, put everything together and it'll all make sense. So if you write down the formula, we know that it's the force of gravity is equal to G M1 M2 over R squared. And Coulomb's law is Fe is equal to K Q1 Q2 over R squared. Very similar. The constants in the case of gravity is G and K for Coulomb's law. This is the force of gravity. This is electrostatic force. And now this bottom part is the tricky part. Sorry about this. I forgot to remove it. This is probably why you guys can't see very well. So gravity is the force between two objects of what? If you can complete that sentence. Gravity is a force felt between two objects that have a mass. Whereas Coulomb's law, or electrostatic force, is a force acting on an object between two objects that have a charge. Exactly. So conditions for use is objects need to have a mass. Objects have mass. Here is objects have a charge.
It's FL or
Fe for electrostatic. Any questions about this? Because now we're going to go into some examples. So here we are. We have three charged objects. The one at the top is positively charged. The ones at the bottom are negatively charged. If you had to draw the vectors resulting from each interaction, how would it look like? Let's take Q1, for example, first. What is the force that it's going to feel with this? Going to be attracted or repulsed? It's going to be attracted. So, what I want you guys to do is to draw an arrow there, because it's being attracted. What is the force that it's going to feel from that? Attraction. Is it equal to this or less? Less, because this is a bigger charge than this. So you're going to draw another arrow here, but maybe a little bit shorter. It's not gas. So if we were to take the resulting force on this charge, what would the vector look like? Down, straight down? A bit closer to there? Absolutely. Okay? You guys understand why? Can you guys do that for the other two charges? If you had to calculate, the second part of this is telling you calculate the magnitude and direction of the force acting on Q3. So that means what I'm asking for, what this question is asking for is this. Can you find the direction and the magnitude of that arrow? Think about just vectors. This is just a vector problem. And the forces, you calculate using KQ1, Q2 over R squared. Do it. Yeah.
Lui est moins vite, fait qu'il va être plus poussé de ce bord-là puis attiré par ce côté-là. Fait qu'il va aller comme dans le milieu, mais plus par en bas.
Ouais, exactement.
Ok.
Ouais. Don't forget, I'm asking you for the magnitude and the direction. So you have to break it apart into x and y. What's that? Can you use it here? Yeah, you can use cosine. Those, yeah, all angles are the same.
Cette formule-là, tu peux
I'm showing you the
Okay.
l'hiver sont négatifs.
So negative and positive. Well, it's going to attract our pressure. You decide some positive direction. So it's because you know this is attract. You establish a negative direction. I mean, I don't know how you guys learned this in high school and how you guys learned this in CJ, but I have a trick to make these vector calculations to be a little bit more simple. Do you guys ever use tables? Like this? Have you ever seen that before? Yeah? So if I have F between Q1 and Q3, and F between Q2 and Q3, and I add them up, I should be able to get F net for Q3. Okay? So let's say I have the interaction between this and this. I need to establish that that's my frame of reference. Are we okay with that? If that's my frame of reference, anything, so in this case, the attraction force is in this direction, right? So is it going to be in the positive or negative x direction? Negative x direction, positive y direction. Are we in agreement with that? So I just need to fill this table in. So I have F between Q1 and Q2, so it's going to be K times 4.0 times 10 to the negative 6 coulombs times negative 6.0 times 10 to the negative 6 coulombs divided by 1.2 squared multiplied by, I'm going to make a table, multiplied by cosine or sine of angle. Because I'm looking for the x direction, so this is going to be what compared to that? So that was cosine, right? So cosine is 60. So that would give me the first force on the x direction. I just have to write the same thing for the y direction here. K Q1 Q3 over r squared times sine 60 degrees. This is going to be a negative number. This is going to be a negative number because it's going in the negative x direction. So here's the same thing, f q2 q3 over r squared times cosine 60. But this time, is it going to be positive or negative? Is this force going in the positive x or negative x? Positive x. Oh, it's not cosine 60. It's just that because there's no y here. There's y. So then I add these two to get this. I add these two to get this. I'm not sure if you guys learned it that way. If you have a different way of doing it, I don't care. Do it your way. Yep. So which one? It's because G is established y axis. Right? If you want to do it like that, this is here. Or you can say you can say this. I'm here to help you guys, okay? So put up your hand if you're showing the class with no idea what's going on. If you understand it, we can move on to the next slide with more examples. Yeah. There's no example to it.
This little.
So, between Q2 and Q3, this is asking you the net force by you're saying there seems to be a mistake with you can't see the problems, right? Technology. We'll just do them on the board together. It's going to be too long for me to upload them right now. Let's move on. I'm posting the next problem up for those of you who want to do it. I'm going to wait 2 more minutes for those who are working still on the first problem. Okay?
The MC it's 10 to
-3.
-3.
Yeah. So this is, I don't have a number for you. If you wanted to solve this second question, you should have this equation. So we said that F net, whoopsies, F net is equal to the electrostatic repulsion, which is sending this particle this way, minus the friction, which is going to prevent or oppose the direction of motion. All right. So now that's the main equation that we need to know. Because it's on x, everything's happening on the x-axis here. We don't need to separate this into x and y. It's a simple one-dimensional problem. And so we have the electrostatic force minus the coefficient, the force of friction, divided by mass to give you the acceleration. Okay? It ends up giving you some humongous number. Yep. It's big. The charge is bigger than I thought I would make it. Yeah.
No, that's it. Put your hands up if you have a big one. Did you say that?
No, I said if you have one, it's okay.
Oh, okay.
Here is question 3.
Mais le 1, j'étais capable de voir, mais le 2, ça va être une fois.
Fait que tu vois, la force, c'est quoi le.
Ouais, parce que j'avais manqué un
So,
C'est 50 ou 5.0?
Ça a l'air d'être 50. Il y a pas
Il y a
de
un petit
point.
point là. Il y avait des points à côté là, c'est là, c'est stretch.
Je demanderai après.
Check, loading. Il y a une petite balle qui vole.
L'accélération, c'est 0.
Is it 5.0 or 50? Because the
50.
Okay.
Yeah, 50 points. I did a pointer, so for significant. Well, you know that.
So we still are gravitational
Yeah.
One more problem before I break, okay, guys? Can I change this? Try an example number 4. This one is a bit harder. Those are equal charge. So that means there's a repulsion or charge. Now, if you notice, there's only one thing contributing to the y direction. The mass. So the force of gravity is the only thing that's opposing is Ty, the tension on the y-axis. So if you have the angle, and you have Ty, it's like Ty is equal to the force of gravity, you have T as well. That will be the force of gravity. Is anyone stuck on number 1, 2, and 3? I need to help you if you are. Okay? Don't be afraid to say it. Failing the class is worse than putting up your hand right now.
Avec la force de l'impulsion. Avec l'eau, ça fait pas de circulation. Mais on doit prendre
That one and all Once you're done this question, take a break, come back at 8 concepts.
Il y a plus de cours de vie maintenant, je sais pas besoin de faire Mais moi, je dis par
Thank you.
Okay, guys, everyone have your seats. I just want to touch base with you guys. Is there anyone who is like, what language are we speaking here? Okay, anyone? Don't be afraid to say it. I need to know this information because that's the helpful. Okay, so everyone's on the same page. I will post the answers for these once we're done class. I can go around time. I'll post them on your Moodle. What I want you guys to do, I think that's it for my question. Is there a question? Okay, I want you guys to do question 5. After you do question 5, there is another whole problem sheet that summarizes all 3 topics that we've done so far. All right, so we did 3 PowerPoints. This is the 3rd one. There is a problem sheet on Moodle. It's called Coulomb's Law of Practice. I want you to download that. There's answers at the bottom. Again, I have no guarantees that those answers are correct because they're not mine. If you have an issue because you're not getting that answer and you're sure that that one is wrong, come and see me. That's normal. That the textbook's answers are wrong. It's totally normal. And as long as you're correct, I can take a look at your work and tell you if the textbook is wrong or if you made a small mistake. Okay? So first thing I want you to do is try example 5. It's on the board right now. And then once you've done example 5, go into Moodle, do the practice problems. That's going to take us for the rest of the period, okay? I want you guys to stay and practice those, so please don't leave. It's not class is not over. It's a matter of working out those problems. Okay? Go. First thing you've got, do you know the massive So what's going on? This is draw, so where are the negative So you're saying
But what's the short-term meaning? Because I mean, if they're all the same distance, they're all going to get the same distance. What is the charge at V in order for C to be station? Because I don't know how else to resolve it.
C'est avec le monde, ça fait.
Mine are almost dead. It's still working. Shouldn't be that big,